Hiya! So in this video, we're going to talk about directional derivatives. And basically the idea here is to encapsulate this idea of conservative vector field coming from this, or in particular, these tangent spaces. So remember how here, last video, we were talking about how we have this function f, and if I'm looking at the tangents at these f, like the one that increases the function the most, you can kind of see this is giving us some direction at some point. So this is, in essence, the idea of a directional derivative. So we're going to let f be some smooth function on affine space. We're going to let v be some tangent vector at the point. So I'm not necessarily taking the one that's increased. We're just going to take an arbitrary one. And now the directional derivative of f at p along v. So here we need three things, right? So we want f, the function, p, the point, and v is the direction vector. And since we have these three things, that's why we encapsulate all that information in this notation. And what is this equal to? This you might remember from previous years, but this is just equal to the gradient of f of p times the dot. So here the dot product of v. Here remember that we're assuming that the vectors are over an orthonormal basis, which means the inner product is a dot product. So here we can just look at the dot product, and that's okay. And so here, when we look at the gradient times the vector, since it is just a dot product, what do we end up having? Well, the gradient has the derivatives as the coefficients, x1, and this, remember, is going to give us a function in xy, so we'll just apply that to the point p. And then we have v1 for our vector, v1. And so we just do this all the way up to xn, or vn, or however you want to say it. So this gives us the directional derivative of f at p along v. So in other words, so if we look at like w being the vector field, this is going to be kind of the maximal one at this point. So in essence, what we have here is that dw of f, so here w is the vector field, and f is our function. Then in other words, all this is df dx1, right? So partial of f over partial of x1 applied to h1, and then we just keep this going. F xn hn. Here the h's, if you recall, this is precisely w of f is h1. Did I do it w of f or just w? Oh, w of p, sorry. I was like, wait, this feels wrong. W of p? Yeah, because this is the things. And then e1 all the way up to hn en. So here, since we're doing the dot product, right, this h is really encapsulating this h, and here this h, it's h1 x1 to xn, right? So this is, I'm shortening the notation a little to have it fit, but in essence, this is h1 evaluated at p. So we have this, and we'll do a quick example before ending this video. So what we're gonna do is look at the previous example. So we're gonna let f be the function x squared plus y squared divided by 2. And here we already saw this graph. This is kind of like that cylindrical shape thingy, the bowl looking thing. And we already saw that it has a conservative vector field associated to it, given by this vector field. And the question is, what is the directional derivative of f along w? So here we already have the formula from 2.5, so literally right above. So we can just literally just copy and paste. So here, this is df dx1 h1, and there's two of these. So here I guess it's just x, and here we'll do hx plus f y hy. So what is this? Df and dx we already calculated, right? This is x and this is y, right? Now what's h1 and h2? This we also calculated, right? This we calculated last time. Let's kind of go back and see here. Where did it go? Here. So here we have h1 and h2. So in other words, we can just use these. So this is also h, this is x, and this is y. So in other words, this is just equal to x times x plus y times y. So it's x squared plus y squared. In other words, the slope of f is going to increase quadratically as we go further from the origin. So therefore, the slope of f increases quadratically. In other words, by a power of 2, as we get further from the origin, right? And we kind of saw this. So if we look at the vector field here, you can kind of see as we get further away, it gets bigger faster. And that's what this quadratic idea is getting, that it's getting bigger and faster. So we can do the same thing with w tilde. So what is w tilde of f? So again, here we're going to write this out, hx plus y, hy. So what are these? Well, the derivative in this case is the same derivative of f from before. So here, the thing to remember is we're taking f to be our function here. So remember the derivative in this case, this doesn't change. So this is still x and this is still y. And this h of x is coming from this coefficient here. So in other words, what we have is that this is equal to x times minus y plus y times x. So in other words, we have minus xy plus xy is equal to 0. So basically, the directional derivative of f along omega of w tilde is nothing. Like, it doesn't really give us anything. What this is basically saying is that as we're moving along the vector field w, so what is it saying? What it says, as we move along w, f doesn't change. The value of f doesn't change. So it's kind of weird to think about this because obviously the points are changing, right? So the point is changing, but the value of f doesn't change because we're looking at a different direction, right? Here we're looking at a different direction. So for example, here we're looking down instead of to the left. And so this is kind of the point. And if you kind of look at this, what you'll notice is everything here is orthogonal. So here this is down, they're 90 degrees. This is to the left, this is up. Everything is 90 degrees to the same point on the right. So because of that, you're always going to have that f doesn't really change. So we're going to stop this video here. And next video, we're going to start talking about 0 forms and 1 forms a little more rigorously. And we're going to start getting into it. So I will see you in the next video. Peace.